Okay, in this video I will explain that how a microphone biasing circuit can be simulated through Python programming so that we can design a proper circuit to achieve a significant amount of gain from a microphone. Let's take a look of this particular schematic that this is basically biasing voltage, DC biasing voltage, and this R1 is a resistor which biases the mic condenser, and this Cm is the capacitance offered by the microphone, which I will also refer as a mic condenser. And then from this particular connection we are taking the signal out, and it passes through a electrolytic capacitor and goes through resistance to ground, and this resistance we can also vary to control the gain of the circuit, to control this output voltage. Instead of calling as a gain, I should say the output voltage. So what is basically the working principle of mic condenser? So once input sound wave comes to the mic condenser surface, it basically changes the diaphragm distance between these two diaphragms. In between there is a non-conducting materials, so that the capacitance of the microphone changes, and therefore there will be some voltage fluctuations across this capacitor. That fluctuation is carried out through this particular rest of the circuit. Okay, so to remove the DC component, this DC blocking capacitor is used, and to get the output from there we have used one resistor across which the drops will be taken to any circuit where we want to amplify this analog voltage, which is basically coming across this variable capacitor which is offered by mic condenser. So effectively we can derive this gain expression of this particular circuit. What do I mean basically? That means this voltage is basically depends on the fact that where V is basically input bias voltage, that is we are referring to 5 voltage here because we have used 5 volt, and V output is the voltage at this particular terminal. V output is the voltage at this terminal with respect to the ground. Now its ratio, if we just compute the ratio of these two voltage, take the absolute value, this takes a form of this right hand side, 1 upon 1 minus 1 plus j omega r1 cmcd. This is a complex kind of expression. This can be derived easily. I'm skipping this derivation from this video, but it can be derived. So where these R1 R2 are basically shown over this picture schematic. R1 is a biasing resistance and R2 is a resistance across which we are taking the output. Cm and Cd. Cm is basically mic condenser capacitance and Cd is the DC blocking electrolytic capacitance, and all these expressions, right? So these are all mentioned over here: mic condenser bias resistance, potentiometer resistance. So these are different values we can simulate, and this is one typical values are basically mentioned. And mic condenser typical capacitance varies from 1 to 10 picofarad. I just got it from the mic condenser specification. And CD DC blocking capacitor we used 10 microfarad, that's why I just put it there. There is no scope to change this particular capacitor, only we will vary this R1 and R2 and then see that how the responses varies. This is the Python scripts. Let me import some of the important libraries. NumPy for numerical computation, Matplotlib for plotting the pictures. From Matplotlib I have just used CM. We are just a color mapping concept we will introduce, and these are some of the supporting libraries. Now take a look of the code section 2. This is important. Number of simulation point, that means how many number of points we will simulate over, right, over different axes. That's why it just took that value as n equals to 1000. And R1 value, I just chose R1 as a 1 kilo ohms, R1 as a 1 kilo ohms, CD is equals to 10 microfarad, that's why it is 10 microfarad, R2 equals to 1 kilo ohm. That means this resistance and effective this resistance across which we are taking the output, we are assuming both of them are equal. Okay, so now the microphone my condenser capacitance is varies from 1 to 10 microfarad. I just took an sample that I'm assuming the capacitance varies from 5 to 10 picofarad. Instead of 1 to 10, I've used 5 to 10 picofarad. Also we could use 1 to 10 as well. Let's see what happened if we just take this one as a 5 to 10. And frequency is basically within the audio range. Especially we focused on the frequency up to 8 kilohertz starting from 20 hertz, and there we need n number of sample points to simulate the experiment. That's why n is there. That means 20 to 8000. Within that range I want n number of sample which are equally spaced. Similarly, capacitance value, so 5 to 10 picofarad, within that I want this is equally spaced n number of sample points to simulate the experiment. Then this mesh grid is created with a value of C and F. Mesh grid means I'm just creating a particular rectangular kind of box over which one axis is C, another axis is F, and we want the grid values. Okay, that's why this mesh grid is created. Now this is basically omega equals to twice into pi. Pi is there within the numpy, so 2 into numpy dot np dot pi, that will give me the value of pi into f. This is basically the angular frequency expression. And from this particular complex expression that has been resolved by this particular kind of segmented calculation, that is imaginary part, real part, and then complex part, and after that these are the equation being computed, and finally this particular denominator magnitude parts, and this G is basically the expression which is the final expression. G is this 1 upon these things. Okay, so now once it is being calculated, this is basically G is basically the objective values which you want to plot with respect to C and F. That means we need to create a three-dimensional plot. That's why subplot is basically these are the normal syntaxes we know exactly from the matplotlib. And projection, we want 3D projection, that's why it is 3 dimensioned over here. And then we are plotting the surface plot. Okay, and the frequencies are basically mapped in terms of the kilohertz, and basically my condenser capacitances are being plotted in picofarad ranges, and this is the G is plotted over here, and all these things are for decorating the curve. And finally this plot is basically I've not stored it, but I can store it using this particular file name. Okay, let me run this code and let me explain what the figure signifies. Yes, this is interesting. So along this axis I have plotted the frequency in kilohertz. As I mentioned, F is basically taken in kilohertz range, F divided by 1000. That means the frequency is starting from 20 hertz to 8 kilohertz. That's why it is there within that. And in this axis my condenser capacitance are varies from 5 to 10 picofarad, and along the z-axis the gain value is plotted. So it is being observed that at this particular combination of 1k and 1k, these two resistances 1k and 1k, these two resistances are 1 and 1k. Yes, 1k and 1k, correct. The gain plot is such that, so what signifies that means it is a three-dimensional surface plot. That means as you can see around 20 kilohertz, if we shift little bit, gain sharply increases. Whatever may be the value of capacitance which is offered by the mic condenser, gain sharply increases. Then this is a flat surface. That means over this particular frequency range, little being shifted from 20 hertz to onwards up to 8 kilohertz, gain is moderately flat. That means all through the capacitance this particular microphone is offering this particular microphone biasing circuit offering the uniform gain. So this signifies, that means uniformity means, how do we understand that these axes and this particular edge and these axes are effectively parallel, as you can see. That means it is cutting, all the corners are cutting to the same level of the z axis. So this is a flat surface. That means if we just select any one of the frequency independent of the capacitance value which is offered by the mic condenser, that depends on basically how much sound pressure is coming there instantaneously, and this will offer uniform gain. Okay, this will offer, let's say this is at 6 kilohertz at 7 picofarad capacitors of the mic condenser, it is offering value of gain equals to, let's say 0.49, correct? So if we shift it to 7 kilohertz, it is also offering the same gain. That means there is no distortions coming from this biasing circuit, and it is independent of the frequency and the capacitance value, right? So this is interesting. So now if we just change different to different combination, R1 equals to 1 kilohertz, R2 equals to 4.7 kilohertz, let me run this code, we will have different amount of gain, correct? So this is around to be 0.495. now the gain little enhances, that is a voltage enhances, output voltage enhances. So in this way we can simulate different combinations, and we can have our choice, which, yes, this is interesting, that if it is 1k and R2 equals to 10k, that means if this is 1k, this is equals to 10k, effectively the gain increases, and you would have almost the same output as it is equal to the biasing of this particular circuit. So in this way we can simulate, and finally we can choose our resistance combinations. So this is all about this particular presentation.